Yeah.
That's what's going on today?
Yeah, that's our lab.
Interesting. And I could grab it up there anyway, but.
any questions before we begin, or any announcements or anything? Questions, comments? I'm a little behind on grading, but I have your quiz graded, so I just need to input those grades. I'll get those back to you, and then I need to work on test corrections still, so don't be too upset if you haven't seen any changes yet. Yeah. Oh, it'll just be like, you'll have a new score in there. But yeah, I haven't done it. Yeah, so it'll just be a new change in there. All right, so I realized last time I forgot to talk about polarity. Yeah, so I think it was chapter 10 homework, the polarity. And so let's figure out, well, first of all, like, what does it mean when something is polar? And so kind of the first step to determining whether something is polar is, of course, right, we examine the bonds. And so let's do that for actually this molecule. So let's look at carbon tetrachloride for a second. And so carbon tetrachloride, so what do we think about these carbon-chlorine bonds? Are they going to be polar, non-polar, just the individual bond? So polar, so I heard 2 votes for polar. And so in chemistry, we draw our arrow going towards where the electrons are being pulled, and sometimes I put a little plus sign on the tail to remind myself this is more positive. And I think physics does the opposite convention. So just be aware of that. And so we're going out in all directions. And so the next kind of step is to establish, is it symmetrical? And so really, if you're in physics, you might understand this from a different perspective. And so once I get my molecule kit together. But you're basically adding up all these vectors. So right, our arrows are showing which way the electrons are going, except it's going out, right, in all. Exactly, right? So it's going out all fully symmetric. And so here I have, so this is obviously methane, but I just wanted to show you this little diagram so we can see, okay, it's fully symmetric, right? We can rotate it, that all looks the same. And so yes, in this case, even though the bonds are polar, the overall molecule is nonpolar since our arrows kind of cancel out. And so, questions?
How do you know when a bond is polar by itself?
So you can take the difference in electronegativity, and if it's greater than 0.4, then that generally starts to mean it's a polar bond. And just as an aside, the ionic, if you remember, was when it was greater than 2. And again, this is just kind of a general guidelines. I'm sure we can find exceptions in the literature. And so the other way, if you're not totally into vectors, or maybe you haven't taken physics, so the vector language doesn't make sense. But this is another good cheat sheet. And so it goes back to what group it falls under. So if we're under the 4-electron pair, and then as long as it has all 4 of these atoms being the same thing, right, then that tells you it's fully symmetric. So all these first rows, so the first column here, these are all fully symmetric, right? So we would expect BF3 to be nonpolar. So anything, right, silicon tetrachloride is nonpolar. PCl5, right, this would be PCl5, that would be nonpolar, and we could write that. So phosphorus tetrachloride, or pentachloride, sorry. I'll just draw this out there. And so this one, right, these bonds could be polar. But overall, because it's fully symmetric, it is nonpolar.
So if one of those chlorines was a fluorine instead, then the molecule would be polar?
Well, fluorine is still pretty close to chlorine in electronegativity, so that would be questionable. Like, I would still say that's more nonpolar. But if we swapped it like with a hydrogen, that would be a better example, since hydrogen is not as electronegative. So yeah, if we swap that, then. And so now we kind of have one-sidedness of where it's more electronegative, right? And then this top part over here is more positive, again, relatively speaking. We can draw our vector arrows to kind of help us see that, so it's going out. And let's see, I'm fishing for a phosphorus. 1, 2, 3. Let's just see if my symmetry. Sorry, I was trying to find a good picture of these, but I'm not finding one. Okay, let's look at another one. So I couldn't find a good 5 example, but they had SF6 on here. And so right, same sort of thing. So if we replace this with a hydrogen, now we would have one side that's more positive, and this side would be more electronegative. So let's write that down. So this would be nonpolar, this is polar. And then again, SF6 for comparison, fully symmetric. What's your question?
And it only has to be polar on one axis. It doesn't have to be polar on all axes.
Right, you're just trying to break the symmetry, essentially. So anytime the symmetry is broken, then that tells us it's probably going to be polar. Yeah.
And is polarity reflected in the actual structure, physical structure? Like, will the, for instance, if you added a hydrogen onto all the chlorines, would they bend away from it?
Well, so they wouldn't like bend away from it really, but it would be probably better represented by the electrostatic potential map or the dipole moment. So let's look at a few examples. So let's look at acetonitrile. That's what I'm trying to spell. Acetonitrile. Oh my gosh, sorry. Where's the Wikipedia page? Wikipedia. So right, we have acetonitrile, so we could draw out the Lewis dot structure, and the key point would be those two little lone pairs. And so then we can see, so if we go down, what we're looking for is the dipole moment. So the dipole moment is a good reflection of how polar it is. So if it has a dipole moment, then it means that it's polar. And so this one has a kind of high dipole moment of 3.92. And then let's just see for comparison if they have, so Wikipedia doesn't have the dipole moment of every compound, but it's pretty good. So methane, dipole moment of 0, so that's kind of expected. And then
And
you,
it has a dipole moment of 0 because it's nonpolar?
exactly, so, and this can kind of maybe help you see like what's, because there's a range of polarity, right? You have things that are like kind of polar, and then things that are really polar, like acetonitrile. And so something that's kind of polar would be these like ethers. And so this is diethyl ether. You could have dimethyl ether. So let's look up an ether. And let's see if they have what we're looking
Oh,
for.
there it is.
So 1.15, so right, we can see the range, and so we can kind of think back to the structure, what that means. And of course, right, it has asymmetry at the oxygen, so we're kind of looking at that point. Obviously, those two lone pairs, so that's where that dipole moment is coming from. And then
If
it,
the oxygen wasn't there, it would be a straight line.
right, and so we could compare, like, let's look at pentane then. So pentane would be like the straight line equivalent, so just carbons. And so, let's see, do they have a dipole moment? Dang, no dipole moment. Question?
If all the bonds were double bonded, it would still be non-polar, right? 'Cause it's like symmetrical.
Yeah, so the bonding doesn't matter whether it's like single, double, triple. You're just looking at like the geometry, and then again looking for symmetry, no symmetry.
So for instance, like if there was two double bonds and one single bond, then it would be polar because it's not symmetrical.
No, it wouldn't matter, right? And because remember with those resonance structures that we said the bonds average out anyways. So let's see. Man, they didn't have no dipole moments for those compounds. Question?
So then acids would have a strong dipole moment?
They should, yeah, so let's see if hydrochloric acid, oh. Yes, I want. So they would be pretty polarized.
Maybe
Oh.
control F, if it's in there.
Yeah, I'm not seeing it. Let's look up. Yeah. I actually would have thought it been higher, but yeah, 1.0, so it's still, you know, somewhat polar.
So that's what gives acid its acidity, is the dipolar moment?
That's a small contributing factor. It's more to the fact that like it disassociates and then, right, that hydrogen can obviously attack other things. And so there's like different ways to measure like the strength of acids, which we won't go into, but you could ask me about later on how they determine that. But yeah, it's basically like how much it wants to give up its proton, and then like looking at that, which is kind of related to electronegativity, right, and all these things, but there's another measurement for that.
So then how would this change if you had like an OH on the end of a,
So yeah, let's look at ethanol then. So we would expect that to be polar, right, especially if it's asymmetrical. And so let's see if we're batting, bad batting average right now on Wikipedia. Come on, have a dipole moment for us. So 1.69, and so again, we can kind of compare. And it's all about, right, that oxygen, how it's off-center. And so other good classic examples are, of course, we can compare them like chloroform to carbon tetrachloride. So we said carbon tetrachloride, oops, was nonpolar. And, oh, I actually drew out dichloromethane. So this is dichloromethane. We could have also drawn out chloroform. And so are these polar, nonpolar?
I think they're both polar because of the chlorine.
They do not have symmetrical electronegativity vectors.
Excellent. So all those answers are good. So, right, we can see that broken symmetry. Vectors, if we want to add that, right, you can add those vectors, see what overall direction they're going. Yeah, breaking symmetry, so all those are good ways to tell polar, nonpolar. Do we feel okay about that? And then I will just mention, not to harp on CO too much, but just if you look at CO, so I would consider this polar, but if you look around on the internet, you will find discrepancies just because people will argue. So if you remember back from what we said last time, right, we said the formal charge was on the carbon. We said that that was really reflective of its structure and that it was odd, but yes, that was what it does. But some people make this argument, it's like, okay, we have this Lewis dot structure, but oxygen is the more electronegative atom, so it's a wash and is nonpolar. I disagree with that, but again, you can find arguments on the internet. I just want you to be aware, but I would consider that polar personally, but again, obviously, right, that's kind of the point of science, is you can argue and debate and look at different ways to measure stuff. All right, I think that's a wrap for chapter 10, unless I missed anything else. No, I'm just glancing back at my, oh, we didn't talk about redox, did we? We forgot about redox. Okay, we should do redox then, because that was pretty important. And so we're doing those double displacements. And so, right, we had said, well, double displacements are not, these are not redox, right? And so let's first say, well, how do we even know what is redox?
Something is oxidized and something is reduced.
I like it. So what does that mean, right? So something's oxidized, something's reduced. So redox.
I like to use oil rig. So oxidation is loss of electrons and reduction is gain of electrons.
I like it. All right, so I will write down oil rig in a second. You were pretty fast. And so anytime for these redox reactions, the important part is we're transferring electrons over. And of course, right, if something is losing electrons, obviously there's something has to be there to gain or accept those electrons. And so blah, blah, blah. And so let's actually skip down. So I think it's better to look at, well, how do we even determine oxidation states? Before we try to figure out who's gaining, who's losing, well, how do we even know where we're starting at? And so these rules are pretty nice, so they help us. And so this is the most important one. And it says, so free elements have an oxidation state of 0. And so this is usually a big hint to me. If I see a free element, they're like, okay, maybe there's going to be an oxidation reduction reaction. Because usually, right, you start with some metal, and then it either donates electrons to something else, and then you get, obviously, ions in solution, or maybe you get out a gas. So anytime you produce a gas like hydrogen, that could mean you have a redox reaction. And so again, notice, right, this is anything in its elemental form. So it could be, right, P4, S8, don't forget about those. So as long as it's by itself, right, elemental form. And obviously, right, all the diatomics, so people remember. And so a lot of this is electronic bookkeeping. And so we start off with our ions. Those are just like before. So, right, they still have their oxidation state equal to their charge. And so all this means is for the ionic compounds, right, this is a measurable charge. But for other things like covalent compounds, these oxidation states are more just, again, like electron bookkeeping and formalities. And then, of course, just like before, right, our oxidation states have to equal 0, or obviously the charge of the atom if we have a charge. And then so kind of these rules, so let's look at these rules. And so they go in priority. And so what it means is fluorine is always, always, always -1, right? And that makes sense. So it's extremely electronegative. So it's always going to be gaining electrons. So you'd never find it in a positive oxidation state. So it's always -1. So you can base your oxidation state off of fluorine. And then after fluorine, our next most reliable is hydrogen. So hydrogen is usually in the 1+ state, except when it's a metal hydride. Sorry, I can't spell anything for some reason. Hydride, right, like aluminum trihydride or something, or some sort of iron hydride, whatever. And so that would be a -1 oxidation state. But usually it says, right, metal hydride, and that "ide" is your clue that, oh, okay, it's a little different. But everything else that we see it in, right, organics, water, blah, 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 it's always 1+. And then our next most reliable is oxygen. So oxygen is always in the -2 oxidation state, except in peroxides. So, right, hydrogen peroxide is obviously one example. And so in that, the whole peroxide is -2. So this is peroxide, and that means, right, each oxygen is -1 by this math. And then any peroxide, and again, in this course, we'll probably just stick to hydrogen peroxide, but eventually you might go on to OChem. And so this is a peroxide group where it's just an O, single bond to another oxygen, and then it's bound to, obviously, hydrogen in this case, or any organic. So R just means anything, so carbon and whatever. So there's like a million organic peroxides that we won't go down the rabbit hole of looking into. And then the rest follow like you expect. So all our group 7s, right, our halogens are -1. And then group 6 tends to be -2, group 5, -3, etc. And then obviously, right, the weird oxidation states in your periodic table can crop up, if we have interesting compounds like II3 or something, then you'd probably have some weird oxidation states. And so let's look at these examples. So then if we look at nitrate, so that's NO3 with a negative charge on it, then we base it off of our oxygen first, because that's the highest on the list. And so if oxygen is -2, that means nitrogen is +5. So again, that's where you get those weird formalities. Sodium chloride is about what you would expect. 1+ for sodium, 1- for chloride. Then obviously, right, group 2 is what we expect, so they should all be in the 2+ oxidation state. Chloride 1-. And so nonmetals higher on the table take priority, so that can help guide you. And so now let's go back and kind of determine, well, what is a redox reaction? What's going on? And so let's analyze this one. And so what's the oxidation state of sodium? So 0. What's sulfur?
Would be also 0.
And then what about in the product? So now sodium is?
And then -2.
Excellent. So now we can start to understand what a redox reaction is truly. And so we can see our metal, and so you're going to notice this right away. Your metals tend to supply your electrons, and so they go to our positive oxidation state. So lose electron. And then you want to practice doing the bookkeeping. So they gave us a balanced reaction. And so each sodium is losing 1 electron, but then it times 2. So we have 2 electrons floating around. And then sulfur, so we see it goes from 0 to 2-. And so it became more negative, so it gained 2 electrons, and then there's just 1 sulfur. And so that all balances out. So 2 gaining, 2 losing. And so let's go back to your oil rig for a second, because now we'll kind of piece all these together. And so let's look at the text, and then we'll do the mnemonic. And so just like we saw, so we have atoms that lose electrons, so that becomes oxidized. So if we go back to our sodium, right, it underwent oxidation. And then atoms that gained electrons are reduced. So of course, in this case up here, right, our sulfur was reduced. And so let's do, so are people familiar with oil rig? People like oil rig? And so let's write that out for people. And oil rig is what I learned, but I grew up in Texas, so obviously we like oil there. So oxidation is losing electrons, reduction is gaining. And then, does anyone have another mnemonic?
The other one is Leo the lion.
Yeah. Yeah, so
Oh, maybe
Leo,
'cause it's longer to say.
and so Leo takes many identities. So whatever your favorite fuzzy cat is. So I used to work at a school where our theme was the leopard. So it was Leo the leopard goes grr, but Leo the lion, Leo the whatever goes grr. But same thing, so losing electrons is oxidation. And gaining electrons is reduction. So whichever one you like better, if you like the fossil fuel industry or fuzzy cats better, no. So whichever one, so I would write that down somewhere so you remember. And so let's practice another analysis. So let's do this one. And so what's the oxidation state of iron in this case?
0,
Oxygen,
0.
and then iron and iron oxide.
Oxygen would be -2, and that would mean that iron is positive. What is it? Positive? I can't do the math in my head.
Back it out, back it out. You can also back it out too.
Oh, is it +3?
Yeah, so that's the easiest way to do the math. So right, double check that it matches. So oxygen's -2, that's a good place to start. Then it matches right with our reverse swap trick. So don't let your swap trick fool you. But in this case, it helps us. So since it matches, yep, 3 plus 2 minus. And so we can do our same analysis.
So that means that the name of this is iron 3 oxide?
Yep,
Okay.
so practice our naming. And so that's an important part. Yeah, question?
Could you explain why the iron and oxygen is 0 before the reaction?
Oh, just because it's elemental form. So anything elemental form is just 0. That's like our starting point. And so this case, right, each iron lost 3 electrons, but then we had 4, so times 4, so it looks like a 12 electron process. And then our oxygen, so each one gained 2, but then, right, 3 times 2 is 6, so 6 times 2, so 12, so that worked out as well. And so that's something that we'll do eventually. So I think we do this later. We go back and talk about redox. Honestly, second and third quarter just like blend as one. So I can't remember which quarter, but we'll balance. Third quarter will balance these redox reactions, but at least be aware, right? Same electrons have to be gained as lost.
I find that helpful with reduction too, just it's confusing at first, but if you think of reduction as reducing the charge, I find that helpful because you're gaining electrons.
Oh yeah, because electrons are negatively charged.
And so now if we go back to our double displacement, we could do a quick analysis on how it's not a redox. And so let's just verify. So what's our charge of sodium here?
Sodium would be +1,
And then chloride,
-1,
silver,
+1.
and we can ignore the nitrate for now. We won't do all that. Sodium,
+1,
and then silver here,
also +1,
and chloride.
-1.
And so, right, that's a quick, easy way to tell, okay, yes,
Do you
they,
not just group and like treat the nitrate as like one thing?
I mean, you can in this kind of case, but in other
'Cause it stays a
scenarios,
nitrate
yeah.
on both sides.
But sometimes when you do have redox reactions, right, your nitrate gets oxidized or reduced to something, so that's why, yeah. But yeah, in this case, obviously if it stays the same, then we could just do that. And right, that makes sense. So going back to what we said about double displacement, we said they had to be driven by a precipitate or formation of water. And so it makes sense, right? There's no redox activity that's driving it. And so acid, also not redox. All right, so let's go back to our redox section. Blah, blah, blah. So here's another case. So again, same thing, carbon. In this case goes from 0 to +4 based upon our sulfur. So sulfur, of course, is -2 right under oxygen. And so carbon is oxidized and sulfur was reduced. Blah, blah, blah. And so let's look at some, I didn't put weird examples. And so let's look at a combustion. I'm shocked I didn't put a combustion example on here. I should have just made one up, but then I was feeling lazy. All right, let's look at this one. And so let's do C2H5OH plus oxygen gives us CO2 plus water. And so let's go through these oxidation states and kind of see what happens. And so what we find is, again, this is just a formality. And then right now, at this point in time in this course, so like I said, we're going to revisit it later. So we're going to take a better look at these carbon structures. But right now, if we're just doing this kind of basic analysis, we might get weird oxidation states for carbon because we're not looking at individually, so we're just taking the average. So it's okay if we get a decimal number for carbon. So let's see how this works out. And so I'm going to start with our products because that's a little easier. So hydrogen's 1+, of course, oxygen is -2, so same thing. And this product, so that makes carbon 4+, and then oxygen was 0. And so let's see. So I'm going to break off, right, our OH group. And so that oxygen is -2. That leaves hydrogen as +1.
So the total charge of the.
Yeah, so that,
Is -1?
right, you're talking about hydroxide?
Yes.
Yeah, so this is -1. And then that means that this C2H5 has to equal +1, right? So this is where we're going to get something weird. And so how can we solve for this? So if hydrogen, right, is probably +1 then. So now we have that 5 plus our hydrogens, right, plus 2 carbons has to equal 1+. So everyone still follow. And actually it worked out nicely in this one. So what's our oxidation state for carbon? So carbon -2. So I didn't pick an example where it ended up with a decimal. But again, just be aware that that could happen.
Why does this molecule have to have an overall 0?
Oh, because it's neutral.
Okay.
Yeah, so as long as it's neutral, right, it has to be overall 0. And then, like we saw with our nitrate, that had to equal whatever its charge is. But so now this one is -2. So then we can kind of see what's going on. So carbon is going from -2 to +4, so it's losing electrons. And then oxygen, of course, is going from 0 to 2. we didn't balance it.
So a general rule would be oxygen is generally reduced and anything else that it acts on is usually oxidized.
Yeah, and so let's go back, and so there's, I feel like I'm missing notes. And so with that, so you kind of brought up another point, and so we can then say, so if you have a reducing agent, that means that they're going to be oxidized. And so reducing agents are like potassium, sodium, lithium, right? So anything that's a metal, so obviously metals give up electrons, so oxidation is losing. But then if we have this term agent, right, then again it's telling us that it's supplying the electrons for reducing. And so with that, we also have an oxidizing agent, which is what Madeline was basically alluding to. So if we have an oxidizing agent, that means that it gets reduced. And so of course, an oxidizing agent, one of them would be oxygen. And so that's a good observation. And yes, they generally gained electrons.
So would the halogens also be good?
Yeah, so they would
Oxidizing
tend to be
agents.
like oxidizing agents, so like chlorine, bromine, those would be oxidizing agents. And there are also different classes of chemicals are classified as oxidizers if they're like incredibly oxidizing. So let's look up. So this is, do you remember in lab where we kind of talked about this oxidizing symbol? You may not remember it because we like briefly glossed over it during safety. But now that we've talked about redox, so this comes back in. And so if it's right oxidizing, then it's
It will steal your electrons.
yeah, but then right that's also a danger for storage. So that's also what I'm trying to get at is these are kind of dangerous. You have to store them, you know, safely, make sure they don't get out and corrode other chemicals. You don't want to store oxidizers with reducers because right they'll mix just even in the cabinet.
So you would not want to store an oxidizing agent in a metal container, right? Because
Yeah.
metals typically give up electrons.
Yeah, and so that's, well, and that's kind of the problem with like fluorine and chlorine is they're pretty corrosive anyway. But yeah, like nitric acid, so that's an oxidizer. So you want to store that in a glass bottle. But this also brings up other issues. So because nitric acid is an oxidizer, you don't want to mix it with other acids either, because that could, well, if you mix nitric acid and HCl, that actually makes a cleaning solution known as aqua regia. And so that's what dissolves like gold. And so if you look up, this is like how some people back when like the Nazis were going around raiding, they would dissolve like their metals in aqua regia and they're like, oh, it's just an orange solution of nothing. But the problem with this is you can't store this like long term, especially in a pressurized like sealed container. And so this happened, not to me, but some other chemists that I knew, that they were just happily working in the fume hood one day. Explosion goes off. They have no idea what the heck happened. And then they were okay. But it turned out that someone had tried to store aqua regia as a cleaning solution long term. But again, you can't do that. And so, yeah, it did, you know, again, strong oxidizer. So it's going to start reacting and eventually explode. And so that's also why nitric acid has to be kept separate. So you generally don't want to make like nitric acid waste. You don't want to mix nitric acid with anything. You just ideally want to neutralize it and deal with it. All right, I think.
What about aqua regia makes it more oxidizing as it sits?
I think it just starts like reacting over time and building up gases or something, and then it explodes. Because it also depends like what's around it, what it was like, what the solution is. So.
For why were they storing aqua regia?
Well, they thought they were gonna clean later with it, but it's something that you have to make instantly and then quench. Like you never want to make it and then like, oh yeah, I'll leave it for later. It's like you use it, you make it. That's it. All right. Do we feel okay about redox? All right. I think we're ready to go to chapter 11. And so chapter 11, bless you. Chapter 11 is basically what I would consider kind of the bread and butter of being like a chemist or being especially like a synthetic chemist, which is a lot of chemists, right? So all organic chemists, all inorganic chemists. Because every day you're going to be doing reactions, right? So you do a reaction and then you got to figure out how much stuff do I need to add in my flask? Do I have enough? You know, how much am I going to make? What scale? All that. And so now we need to figure out first, what is a mole? What is a formula? Mass? What is all of this? And so let's take a step back for a second. And let's see, did I put a periodic table up? Probably not. And so let me grab a periodic table. And so we have to think about where they were historically. And so we were talking a lot about ratios, right? Like when they were trying to do the law of definite proportions and all that. So they just had these mass ratios. And obviously I can't find a periodic table.
ptable.com. That's what I always use.
Here we
on the
go.
internet.
I was just trying to find one in my notes. And so, right, they were trying to figure out kind of what standard they should do. And then they kind of had these relative weights. And so basically, right, they decided, well, let's set carbon. And so this is where your numbers come in. So we're going to set, right, carbon 12, so our isotope of carbon 12. So that's going to be 12 AMU. But then I also want it to be, so we can talk about this new quantity of moles. Because again, they're seeing everything's in the same ratio, but we have to be able to talk about a quantity that we can kind of see, basically. And they wanted to make it easy, too. So they wanted you to be able to look at this periodic table and know the mass of both an atom and also a mole. So they said, let's set this 12 carbon then. We're going to say 1 mole of it is 12 grams. And so now we can do a very small, at least, derivation. And so we have, well, I want 12 AMU times some factor to give me 12 grams per mole. And so let's look up what an AMU is. And so then we can say, so 12 AMUs, and then we need to convert to grams. And so 1 AMU is 1.66, and I'm going to round, but I probably shouldn't round. So times 10 to the negative 24 grams. So then let's kind of set this up. So we have to do our conversion. So 1 AMU is equal to this grams. And then we need to say by some factor of x, which is going to end up being Avogadro's number. But again, that's how they got there. And so let's solve for our x. So what's our, how many molecules in a mole, basically? Oh. Sorry, let me fire up my calculator. And so now I'm just going to put, so let's get, so 12 times 1.6605 times 10 to the negative 24th. So we need that to equal 12. So now I'll do 12 divided by this. And so we get it pretty close, so right, there's gonna be some rounding issues. They've also have changed Avogadro's number slightly, but we should get something about this. So 6.022 times 10 to the 23rd. Then our factor, right, is gonna be moles or molecules, however many things, or, sorry, atoms, I shouldn't have put moles, atoms, molecules. So that equals 1 mole. So that's how they defined it. And so now they had a way to talk about, right, one individual atom. We can talk about 1 mole. So now this is, right, a quantity that we can hold and see. So 12 grams, right, that also makes sense to us. We can measure out 12 grams. And so this is how we got to a mole. And so if you didn't already pick up the mole highway, I would definitely pick it up. And so it's up at the front. So it kind of helps us kind of navigate our way around. It's pretty useful. So right, our mole is just defined as 6.022 times 10 to the 23 atoms or molecules of whatever substance. And so this is, again, just kind of the mass of everything. And so conveniently, again, they wanted to make it convenient. And so then that means for our molecular mass, we can either talk about one individual molecule of water. And, right, your numbers can vary depending on your rounding, right? You could round this to 1, you could round this to 1.088 or 1.008, sorry. So whatever you do, right? So there's going to be some difference in numbers. You could round this to 15.99. That's fine. I'm just throwing it out there that people are going to have slightly different numbers depending where you pull it from. But all we do is, right, we add up everything from our periodic table, multiply it by the appropriate amount, and then get our mass. And then, right, if it's 18 AMU, then it's also 1 mole of water has a molecular mass of 18.02 grams. So that's pretty nice. All right, now see.
So then would you not be able to just measure, like my water weighs 18 grams, that means I have 18 moles.
Or 1 mole, yeah. You were saying,
You're
yeah,
right,
yeah,
you're right, I had it backwards in my head.
yeah. No, you were, but yeah, that's the whole point is, so we have to have some way of relating things, our mole-mole ratio, and this will eventually take us into, right, stoichiometry and how our balanced equation basically gives us our recipe so that we can, right, measure our water and know how much to add, relatively speaking, or whatever other chemical we're interested in. All right, so try this first one, so see if you can figure out what to do. And again, you should be able to figure it out with dimensional analysis, kind of playing around. But otherwise, right, look at your mole highway. It is there to help you. It can make you feel better about your dimensional analysis. Oh, and then also at the front are solubility rules. So you may want those from last week with those precipitation reactions. Oh, sorry. And then does anyone want to throw what they did on the board for us? I think fine. I think the black is functioning.
So, let's go. We have carbon has a AME of 12. Do you want me to do just 12 or do the whole one?
Yeah, 12 is fine. You're talking about like 12.011 or whatever. Either way.
So for every 12 grams of carbon, there is 1 mole. I kind of did this backwards, but that's okay.
What?
Doesn't
Yeah, you
matter.
need the 35 on top though, or else you get it. And then use your dimensional analysis.
Dimensional analysis.
Yeah, because you had your conversion factor, right? 12 grams is equal to 1 mole. And then so you know you need grams on bottom to cancel out your
Yep.
35.55.
And then we need 1 mole cross analysis. It will be on the bottom, 12 grams.
And then if you're online, you can post your answer.
2.96.
That look. And then you might want to give it a 4th sig fig just because we have 4 if we're being proper here. So 2.963. So that looks good. Any questions on that one? Again, we have, right, use your dimensional analysis, use your mole highway, so whatever feels good to you. Right, so we have moles, so we're trying to go mass to moles, so then it tells us, right, follow this arrow, divide by molecular weight, and that's exactly what he did up there, so dividing by our molecular weight, or again, think of your dimensional analysis, grams canceling. And excellent, so I see chat got the same answer as well. All right, let's try the next one then. So 0.227 moles, how much does that weigh of silicon tetrachloride? And some, yeah. Oh, because of the board. And then, yeah, you can start looking at the next one. So, someone wants to volunteer for this one while you puzzle over the next one. chat. If you have the answers, you can also post them. Does someone want to do the 0.227 moles of silicon tetrachloride? See if anybody else wants to volunteer. Okay, go for it.
Black one is working.
Yeah.
I didn't memorize that molecular weight. So first, I just found the molecular weight of that silicon tetrachloride. And I just added the one silicon molecular mass to chlorine's times 4. And then I just took that number. And then I just multiplied it by 0.227 moles. About 38.6 grams. Does that look right?
Yeah, that's about what I
Hope so.
Question? Oh, sorry. You want to
Oh,
or
it so
rotate the
she can
board?
see.
Yeah.
That better?
I know. Now we got to
Another point?
roll it across the classroom, Vanna White style or something. All right, that looks good. Do we still need some? We probably need some time for this one, maybe. Okay, I'll give people another minute or two to at least make some progress. And we might want to tag team this to put on the board. And then looking also online if they would like to help tag team with our aspirin question. Sorry?
I can start on the first part if anyone else wants to.
Yeah, you can go.
Still working.
Yeah, I think people still need. If you want to give people, let's give people another minute or so. Can I flip this forward? All right, Vaughn, if you wanted to start putting.
Yeah. So, first we want to write down our formula. And then
So did you got 180?
yep, 180 grams per mil. And then we're going from milligrams. So we're going to have to do two conversions. So 30 milligrams times equals 1 gram. And then that makes sense to everybody. Zero, zero, one.
Point 0 1.
0, 0, 1.
Point.
Yeah.
How many zeros?
2.
I think I have a different.
Oh, you know what? I did do something wrong. I had it in my calculator as dividing 180 instead of 30. That's a calculator error. Yeah, it is. Not that, it's 1.6.
All right. Yeah, I like that answer. So did everybody get to this point at least? So 1.66 times 10 to the negative fourth moles. So is everybody here at least? Let's try to make sure I see. So right, did you follow with the conversion to grams? So first just doing that gram setup and then just dividing by the molecular weight, again with dimensional analysis. And so this is a good spot to be at. And so does anyone, oh, so let's see. We actually didn't finish answering the problem. So do you want to take us to molecules?
Yep, we can do that. So
We just multiply by Avogadro's number, right?
Yeah.
Okay.
And you can help tag team.
So for every mole of aspirin, so we have 1.66 10 to the 4 moles of aspirin, and for every mole of aspirin, we have 9 moles of oxygen.
Oh, I thought we were doing molecules.
Yeah,
of
take it
aspirin.
to molecules. So that's not wrong. So right, look, you could do it this way too, right? So you could go straight from moles and then find moles of everything. That totally works. But yeah, let's do the molecule one. I just wanted to point out that that wasn't like wrong.
I misread the question.
Oh,
So, yeah, and then we just take that 1.66 times 10 to the 4th moles. And there is, someone wants to give me Avogadro's constant.
6.022 times 10 to the 23rd.
One mole.
oops.
And I can also give you what the calculator says.
Go ahead.
It's 1.00, and I'm rounding up to 4. Times 10 to the 20th.
All right, so is everybody here then? So I see. I like your A-OK. And does anybody want to tag in, or do you want to just finish us off with the ratios?
If anyone wants to tag in. Yeah, so we have this many. This makes our life easier.
Oh yeah, that's true. You can just do some mental math.
So then oxygen, we have, or carbon, let's start with carbon. Carbon, we have 9 times this amount of molecules, so it's going to be, because I can't do that many decimal places in my head.
Sure you can.
I traded being able to factor things in my head for basic arithmetic.
It's just 9 times this.
9.033.
36.
And now you're being too precise.
Oh yeah. This would be 4. Oxygen would be 8 times that.
Would be what?
8 times
8 or 4?
For
hydrogen.
Oh, hydrogen. Sorry, I thought you were doing oxygen.
I did say oxygen. I meant hydrogen.
So 4.
So this would be 8.03 times 10 to the 20th. And then oxygen would be, this one I can do in my head, is 0, 1 times 10 to the 20th.
Yep. So that looks good. Okay, I was looking at all of them. So oxygen. What do you have for oxygen?
4.01.
Oh, okay.
It should be 2, because 16.
Yeah. Joule. What's your middle one?
that's
8
hydrogen.
point.
Oh, okay. I'm no longer confused. So that looks good. Do we all have this? Do you have questions back there?
I lost track of what happened at the, like, to get to the not, like, to the end of it.
Yeah. So if we're thinking, we found how many moles we have, then we found how many molecules we have, and then in every molecule there's going to be 9 carbons, 8 hydrogens, and 4 oxygens. So if we want to find how many of each atom we have, we multiply this by this number.
Thank you.
Yeah, so you just make your conversion factor right, however many you have. And so that's kind of what I set up over here formally, right? For every 9 carbons, we had 1 aspirin. There's 4 oxygens and 1 aspirin, 8 hydrogens and 1 aspirin. And then, of course, you could finish the proper dimensional analysis, but other questions on this one? All right, let's keep. And so now we also have just our composition of compounds. So of course, right, we can find our molecular formula, but then we can also indicate our relative quantities from a percentage. And so this is useful. So we'll talk about it more kind of vaguely right now. So right, this is just kind of in general. We can find the percent of each element in a compound. So obviously, right, we have the formula, and then you get the experimental mass analysis of the compound, which we'll have to talk about how wonderful it is. And so what this is useful for is we want to, of course, get our whole number ratio of atoms from our elements in a compound. And so they mention this technique here. So it can be determined from elemental analysis. And so I just want to talk about what elemental analysis is. And so it's actually a really powerful technique in chemistry. And it may sound kind of stupid. And so, right, basically you take your compound, and you need to do this to get published. And so you send it off to some laboratory. They stick it in a glove box. They load it into their special little furnace, burn the crap out of it, and then it usually tells you percent carbon, hydrogen, and nitrogen. And then, of course, right, you know what your molecule is, at least, you know, in theory you do, because hopefully you have a crystal structure, hopefully you have an NMR, hopefully you characterize this. And the elemental analysis, why it's so important, is because it also tells you purity. And so I forget the standards, but basically every journal has some sort of standard for the elemental analysis. So it can only be off by a certain percentage. And if it's not, you cannot publish. And this is often the hardest piece of data to acquire, just because your sample has to be super pure. Like when I was doing this from personal experience, like I would take a pure compound that looked pretty pure, and then I would recrystallize it and send that off. Like that, it has to be really, really pure. But, you know, why does it matter so much? Well, because there have been cases, right, where somebody thought they had a compound. They thought they made an iron compound, I think it was. No, vanadium. I think it was vanadium. It was probably iron. Well, I forgot now which one it was. But I want to say they thought they were making an iron compound. And it looked great with the crystal structure. But of course, the problem with the crystal structure is you can only get such high resolution. And so it was contaminated, again, they didn't know this, but it was contaminated with vanadium, except, right, they're pretty similar in size. So on an X-ray crystallography data, they would look about the same. So they'd be pretty hard to distinguish. And if you thought you made an iron compound, you know, that's probably what you think. But the problem came up in the elemental analysis. So they could not get the elemental analysis to hit. So it was off. And so that was a clue. And then later, they did some analysis and figured out that actually their iron chloride source was contaminated, and that led to actually the vanadium compound being more favorable. And so that was kind of weird, but right, that's why it's important, and that's why chemistry has all these different standards, right? You have to characterize a new compound by all these different methods to really prove that you made what you think you made, and that's really, it's really hard, but it's also really powerful and really cool.
Could you scooch back up for a second just to those two things that have been used to find the percent of each element in the compound?
Yeah, so that's just the basic, right, figuring out how much you have of one element over the total compound, so always just part over whole. And so, of course, right, going back to the elemental analysis, you would know. And so chemists don't add up molecular weights by hand once you get to like the experimental research stage. You usually draw it in this program called ChemDraw, and that's because it also gives you like, not only does it do the math way better than we do it with our rounding, but it gives you the isotopic pattern, so that's useful. All right. And so we'll do some math with this. So this will be kind of the harder math that we do is this combustion analysis. And so again, from this, we'll get our percent composition, and we can only get our empirical formula. So this gives us a ratio, but it doesn't necessarily tell us the exact formula. And so what I mean by this, so let's say we were trying to do the analysis of benzene, except in doing the analysis, we could only get the ratio. So we would only be able to calculate a 1-to-1 carbon to hydrogen, right? But then we don't know the true formula, so we don't know the molecular formula.
You don't know that there's 6 of each. There could be 3,000 of each.
Yeah, exactly. And so that's where you have to take in the different techniques. So we would have to do our percent combustion, get our ratio, and then we'd probably want to shoot it in a mass spec. And then that would give us the total mass, so we'd know, oh, there's 6 as opposed to 3,000 or 3, yeah. So all these techniques. All right, so now this kind of goes through how we'll analyze this, and we'll go through all this together. And so the first thing is if we're not given grams, then we want to just assume we have 100, because we want to make the math easy for us. So, we're going to be looking at some problem. It tells us a percentage, and so we'll just convert percent to grams. And again, that's why we do 100, so we don't have to think too hard. So 24.5% becomes 24.5 grams. And so once we have our grams of every substance, we of course want to find our mole ratio. And so this should remind you of last week's lab, right, where you were finding your molecular formula of magnesium oxide. So that was the same thing you did, right? You found how much magnesium you started with, you added some amount of oxygen, you took their ratios of their mole-mole and got your formula, right, which was hopefully 1-to-1. At least the data I saw from people was really good. And so we'll do that, divide by their molar mass, and so there they walk us through. So of course, if we were looking at 24.5 grams of carbon, divide by 12 to give us moles. And then we did this, or at least we were supposed to. Maybe we didn't really need to because our numbers were easy. But now it says divide by the smallest number of all your moles to obtain the whole number ratio. And then so it says, and this is where things get kind of tricky, and it's like experience and judgment call. But then if we have a result to within 0.1 of a whole number, then we want to just round. Otherwise, then we kind of have to play with our numbers and kind of multiply by some sort of number to make it a whole number. So, right, if we have a 0.5 ratio, try to multiply by 2. If we have 0.33, right, try to multiply by 3, or so on until you have a nice whole number. All right, so let's,
Wait,
oh, sorry.
I still am writing. Sorry.
I'll back out for a second. So I'll let people look at this. Well, people also finish copying. But then we'll walk through this one kind of together, step by step. All right, so go ahead and write the problem. So a compound containing nitrogen and oxygen is decomposed in the lab, and you have 24.5 grams of nitrogen and 70 grams of oxygen. And so just take a minute to think about it. How would you approach it? And like I said, then we'll go over it all together, step by step. right, did we all finish copying kind of the guidelines? And then I'll give people a few more seconds to kind of think about this.
Easy enough for a second. Easy enough for a second.
Oh, what's up?
Easy enough for a second.
Oh, zoom out. So you want to see everything again? All right, so let's start going through it. And so I can reference the steps if that helps people. And so, right, first step was just, are we in grams? And so, yes, we're in grams. That's a good first step for us, at least. And so, right, let's convert then those grams to moles. And so that makes sense. And so again, I feel like we should feel comfortable with this. And then the only thing is make sure you're dividing by the individual atom, right? So we're not talking about diatomic nitrogen and oxygen. We're talking about just their individual atoms. So nitrogen is going to be 14, and oxygen 16 or 15.99, whatever you want to use. So in this case, don't double it. So 1 mole, so 14 grams about for nitrogen. And so I get 1.75 moles of nitrogen. Just making sure I get your affirmation so I know.
Yes, that's what I got.
Excellent. And then we'll repeat that for oxygen. And again, your number could vary slightly. So I'm going to use the rounded 16. And so do we get 4.375 for that one? So I see a bunch of nods. Thank you. And so, right, this is a good place to be. So we have moles of each. And so now, right, the next step says divide by the smallest. And so that means we're going to divide by 1.75 to try to get our whole number. So obviously, the nitrogen goes to 1. Let me just clearly put nitrogen and oxygen. And so let's see what that gives us. So 2.5. And so if we have a nice number like 2.5, we want to just multiply then by 2. And so I'll just do that. So I'm trying to indicate it the best way. So maybe I'll rewrite it. So now we're here. And so nitrogen is a 1 ratio. Oxygen 2.5. So now we'll say all of that times 2 to give us our whole numbers and our formula. So that would be dinitrogen pentaoxide then. So that was a pretty nice one with numbers. Any questions about this one? And so like you all were saying, and I think you're picking up on the fact, so of course, right, we have, this is obviously just our lowest ratio, lowest whole number ratios, so our empirical formula. It could be the same as the molecular formula, right? It probably is in this case. We are familiar with dinitrogen pentaoxide. But, right, we need some sort of true verification. And so again, right, it's just a multiple of the formula. And so they kind of have us formally, they show you what the formula would be. So obviously your molecular formula is just your empirical times whatever positive whole number integer. And again, right, we have to be given the molecular mass. Likely this would be done by a mass spec. and then we'll just be given the answer in a problem. All right, so let's look at this combustion analysis. I think we have enough time for this. And so this is what I was talking about with the elemental analysis. So this would be the same thing. So you can put / elemental analysis. So that's usually what chemists are talking about. And usually they're going to be crying because they're like, oh man, I got to make elemental analysis. So I got to repurify this substance. And so, right, again, it's generally used for organic compounds because it's going to be a bunch of organic chemist researchers and also organometallic chemists. So anybody that's making molecules and making new ones has to do this. So that's a lot of people. And then, so then we'll see how to do this combustion analysis. And so this is kind of interesting. Again, we'll go through this together. And so, of course, we'll know our initial mass of our product, and then we can figure out what we make. And so part of this, and so let's kind of look at, right, a general reaction. So we have some sort of organic, so carbon, hydrogen, oxygen, right, we don't know what they are. And then obviously we're going to burn it with excess O2 to give us CO2 and water. And so, right, what it's telling us is, okay, well, how can we figure this out? Well, we're going to get some amount of CO2 out. And so this is kind of the key point. So all our original carbon forms our CO2, right? So that makes sense. That's the only place carbon goes. And then looking, the other hint is then, well, our hydrogen forms water, okay? And then we'll have to figure out oxygen at the end. And so we'll see what this means, but basically we'll figure out how much of our mass is from carbon and hydrogen, and then we'll figure out oxygen. And then, of course, just like we did before, right, we'll divide by the smallest and figure out our empirical formula again. And so this is what I was talking about, that usually these are nice fancy setups. And so I'm not sure how all the elemental analysis setups go, but at least in this case, right, basically in all cases there's a furnace where everything is burned in a very controlled manner. And then, of course, all those products are analyzed out. So in this case, there's a water absorber and a CO2 absorber. So personally, I don't know how they determine the percent of nitrogen, so I would have to look into that. All right, so let's look at this one. So this is a little easier in this case. So we'll start with this example. And so, right, we have only carbon and hydrogen, so we don't have to worry about the oxygen stuff. And so let's see what we should do. And again, maybe it's helpful to rewrite what's happening. So carbon and hydrogen give us CO2 and water. And so let's figure out if we want to get moles of carbon in our formula, we first need to figure out, right, moles of CO2. Then that gives us how many atoms of carbon then, and then that gives us back to our formula. And so let's do that. So let's start with CO2, because there's a little caveat with water that you might see, but again, we'll get there when we get there. So 1.83 grams of CO2. And what's the molecular weight of CO2? It's 44, but let's see, 32 plus 12, so yeah, 44. So 44 grams per mole. So first step, find moles of CO2. So 1.83 divided by our molecular weight of CO2. So 1.83 divided by 44. And so I get 0.041, I'll round it to 6 moles of CO2. And so just like we did with the aspirin, right, we can look at our formula. Well, for every 1 mole of CO2, right, there's 1 mole of carbon. And so that means that there is 0.0416 moles of carbon in our original reactant. So does everybody follow? Okay, excellent. And so now let's repeat that for water. I'll zoom out of here. So we had 0.901 grams of water. And of course, right, the molecular weight of water is 18 grams per mole. And so let's just repeat. So this is for water. Divide. And so I get 0.05 moles of water. But then how many moles of hydrogen do we have? What's the difference?
It's double because there's 2 hydrogen.
Excellent. So it's double, right? So does everybody see that? So in this case, we have to multiply times 2 to give us moles of hydrogen. Now 0.1001, that's moles of hydrogen. And so now we're back where we were right from our previous example. And so I'll flip back over so we can remember, right? So we're basically here again, where we have our mole ratios. And so we need to divide by our smallest. So let's go ahead and do that. So we'll be dividing by our carbon. So divide by smallest mole. So I'll put carbon, so I'll do carbon then. I'll show the work. Normally I don't show the work. So that's 1. And then 0.1001 divided by 4. And let's see what kind of a number we get.
I got 2.40, that is rounded to 7.
So 2.4. And so this is where we kind of get a weird scenario. So we have to make kind of a judgment call. So there's 2 different judgment calls we could make at this point. So who has maybe one? And I might round this to 2.4 for ease.
We can round it even more to 2.5.
And so,
Make it easy.
and
That's too much rounding.
yeah, and that's where, I don't want to say, right, that's wrong, but yeah, there might be too much rounding, and so that's all, you know, part of our judgment call. And so let's just say like lots of rounding or more rounding, right? Then we could do this carbon to hydrogen 2.5, which gives us, right, about C2H5. But maybe we can get a better answer. So, right, this would be an okay answer in terms of, you know, right and wrong and all that stuff. And again, that's where showing your work is important, because I really care about, like, can you do the steps? Can you get to here? And this is always tricky. And then what else could we multiply it by? So I say 5. So 5 would be the better one. So times 5. And so, right, kind of noticing, well, 4 times 5 gives me 20, so that will probably give me a whole answer. And so 2.4 times 5, so that's 12. And so our better answer is C5H12, so that's a good answer. And this also matches with the formula of pentane, so that's probably also, again, a good sign. So I'm just showing pentane, so C5H12. That's a happy answer. All right, I think in 10 minutes we can do this next one. And let's see, I'll give you, so let's at least take like maybe 3-4 minutes to start this on your own, see how far you get, and then we'll go over it at the very end. And so ask your neighbor too. This does have the oxygen bit, which we didn't quite cover, but you can still get pretty decently far in this, even if we haven't explicitly gone over it. So what do we do first? Walk me through it.
You divide the grams of carbon dioxide by its molecular weight, which is 44.
So that looks good. So what do people get when we do this?
I got 0.0556.
Is,
And I did round.
oh, no, it's okay, excellent. So moles of CO2. And so where do we go from here?
You do the same thing for the water,
So repeat for water.
except you use 18, because that's its molecular weight.
And using 18. I know, that's like half the hardest part in chemistry is what molecular weight. So how many moles did people get for that one?
I got 0.03335, exactly, according to my calculator.
So I see a bunch of nods as well. And so where do we go from here?
I multiplied it by 2 to get just the hydrogen, which is 0.0667.
667, so moles of hydrogen. And then just so we're clear, right, this was the same for moles of carbon. So did everybody make it to this point at least? So I see a lot of nods. And yes, so this is a good place to be. And so now where do we go from here? Because we hadn't done oxygen. So what might we do? And so remember, right, this is a key little piece of information because they told us how much we had. So what could we do?
Add both of those up and subtract them from it.
Yeah, so you mean add the carbon and hydrogen?
Yeah, subtract it from that one.
Excellent. So let's do that. And so don't forget to multiply by our mass. And so that's perfect though. So 0.0556 moles. So now if we're doing carbon, so times 12. So we get mass of carbon. So I get 0.6672 grams from our carbon. And then repeat that for hydrogen. So I'm going to just multiply it by 1. So that's 0.0667 grams of hydrogen. And then add it just like she said. And then we'll subtract. So this plus 0.0667. And so I have 0.7339 as our carbon hydrogen. And so that's where the subtract to find oxygen mass comes into play. So 0.8233 minus this. And so we should have 0.0894. And so, right, that's grams from oxygen. So 0.0894. So grams of oxygen. So now we have to divide by 16 to give us moles. So now I get 0.00558. So moles of oxygen. And so, right, your moles of oxygen is probably going to be your smallest one. And so now we can go back and do what we are used to doing.
Will you go back and say one more time how you got the grams of oxygen?
So we can start back here. So, right, we have this many moles of carbon, this many moles of hydrogen. And then we said, well, let's figure out mass-wise what this is equivalent to. So we took our moles of carbon, multiplied it by 12, right, to get mass of carbon in our original sample. And then I was kind of quick with the hydrogen because I just rounded to 1. Yeah. So that gave us 0.0667 grams of hydrogen roughly. And then we subtracted, so we added these together and then subtracted that from our original sample mass. And so that's how we got the 0.0894 grams of oxygen. And then, of course, that gives us moles of oxygen. And so once we're at this point, so right, we have moles of carbon, moles of hydrogen. So now we can just divide by our smallest again. So now we're at the finish line here, so divide by smallest mole. So of course, oxygen, I'll just put to 1. Hydrogen, so 0.0667 divided by this. 12 seems like a good place to round it to. And then carbon, so carbon was 0.0556. And I'm going to assume it's going to come out close to 10. I'll punch it in. So 9.96. So that's pretty close to 10. So I felt pretty comfortable just rounding to those nearest whole numbers there, since again they were within the 0.1. And so now I'm pretty comfortable with this formula. So C10, H12, O. And you could put the 1, but. All right, that's a good place to end lecture. And so we'll pick back up on Wednesday with more kind of stoichiometry and more practice there. And then any questions on stream? Otherwise, I'm going to stop the stream in a minute or so here. Oh, thank you.
I kind of got lost at the last part.